This question is about the evolution of a star. State what is meant by the Chandrasekhar limit. Not sure if I'm saying that right. And this actually sets the upper limit for the formation of a white dwarf. So it's the upper limit, mass limit, upper mass limit for a white dwarf. And that's after the supernova. If after supernova there's a mass that is left over is less than 1.4 times the mass of the Sun, then it will remain as a white dwarf. The Oppenheimer-Volkoff limit sets the upper limit on a mass of a neutron star. So that's the upper limit, the mass of a neutron star. If it goes above that, then it will go to a black hole. So suggest how your answers in A can be used to predict the fate of a main sequence star. So after the supernova, so you have a supernova, if the mass left over is less than 1.4 times the mass of the Sun, we have a white dwarf. If it's greater than 1.4, it will form a neutron star. And if it's greater than the Oppenheimer-Volkoff limit, it will form a black hole. Question E4. This question is about the Hubble's constant. Outline the measurements that must be taken in order to determine a value for the Hubble constant. Well, using this formula over here, you can measure the redshift. So you need to measure the redshift to measure the recessional velocity. So what happens here is that you look at light, and we've got this lambda over here. This comes from the lab. We can got that spectrum, emission spectrum, and then from that we can actually measure the delta lambda, which is the Doppler shift. Once we know that, we can measure the v, this v, and this v is your recessional velocity. Once you've got that, then by using other methods such as Cepheid variables or supernova events, we try and measure the distance. Try and measure the distance of a galaxy or stars from a galaxy, stars, galaxies. And we use Cepheid variables, supernova, and so forth to do that. And you repeat that for many galaxies. Many galaxies, clusters of galaxies, you repeat that. And then what happens is you plot the v, and this is the recessional speed against the distance, and the slope of that will be your Hubble's constant. It's constant because it seems to form a proportional value. It says one estimate of the Hubble's constant is 60 kilometers per second per megaparsec. Cygnus A is a radio galaxy at a distance of 6 times 10 to the 8 light years from the Earth. Calculate in kilometers per second the recessional speed of Cygnus A relative to the Earth. So you've got here that your velocity is equal to Hubble's constant times your distance. So we are given that an estimate is 60 there, and this is in kilometers per second, megaparsecs to the megaparsec. And we are going to, this is given in light years, so we're going to have times 6 times 10 to the 8 light years. But to convert a parsec, 1 parsec is equal to 3.26 light years. So we have got megaparsecs. So to convert our light years into parsecs, we actually have to do the reverse. We have to divide through by 3.26. And we've got this mega, and the mega is the inverse, so it's times 10 to the 6 will be there. So when we do that, we get 1.1 times 10 to the 4 kilometers per second.